Thanks to the organizers for inviting me here. So this is a talk, this is a paper joined with my colleague Vitaly Feldman. And it's about is there something I have to turn on, or it actually worked just a while ago. Oh. I hope the computer didn't freeze, because actually now it's IBM, you know. Sorry about that. Yeah, I think it actually froze. Yeah, I'm sorry about that. Oops. Embarrassing. Still alive. I'm not sure if it was some weird interaction between the remote. I don't know. This doesn't happen normally with this computer. I'm restarting, yeah, but I'm worried it was something weird about the remote. Maybe I'll just use... Okay. Okay, sorry about the delay. I hope it doesn't happen again. So, okay, we're talking about approximations by Juntas. So it's a little, there's something outside of the frame. So we're talking about the real valued functions on the Boolean cube, which is maybe a slight difference, not necessarily Boolean functions, but the real valued. And the question is, how well can we approximate function f by a function that depends only on a small number of variables? Oh my God. I really apologize. I think it's something about the USB thing. Okay, so I'll just use, okay. Just to make it clear, we measure the distance between two functions, the LP norm, defined in terms of the expectation. And in this talk, we're talking only about uniform distributions on the cube. So whenever there's some expectation or probability, it's over the uniform distribution. So it's mostly about L2. Sometimes I will refer to other values of P, but for the most part, we care about approximating the function in L2. So right off, let me state Friedgood's theorem, which is a fundamental theorem in this area. And that's a statement for Boolean functions. So Friedgood's theorem says that if you have a Boolean function of small average sensitivity, or equivalently total influence, whereas probably most people here know, average sensitivity is measured by taking a random point and flipping a random bit and checking how often the value changes. And if this quantity is small, then the function can be well approximated by a function of small number of variables. In particular, the number of variables is exponential in the total influence divided by the approximation error epsilon. Now this is measured, I stated the L1 norm here, but for Boolean functions it doesn't matter that much. We just have 0, 1 values. I really don't know what's going on here. Okay, so this talk is about real valued functions, and in particular, it's about several related classes of functions which come from a slightly different angle. So I will say a bit about these classes of functions and why they are interesting. These classes are submodular functions, Xos functions, subadditive functions, and self-bounding functions. And why? Okay, why do we care about these function classes? Well, for one thing, they are mathematically nice. We can prove nice things about them. But this work was really motivated by a question raised by Balkan and Harvey, which comes more from the algorithmic game theory angle, which is given random examples of values of such a function, how well can we learn the function from random examples? And these are the classes of functions that arise in AGT for the following reason, that these are classes that capture certain types of valuation functions of goods. So we have some ground set n, and we talk about subsets of that set n. And these functions might measure how some agent values a certain subset of those items. Okay, so that's the direction where these functions come from, except maybe for the last one, which is self-bounding functions. That one comes from a different direction, but I want to throw it into the mix because it's nicely related to these classes. And I will say why it's also interesting. So I already wasted a lot of time, so let me go pretty quickly over these classes. Submodular functions are functions that exhibit the property of diminishing returns. So here I'm a little bit sloppy about the notation, namely in the game theory world, people talk about set functions. So the argument is a set. Naturally, this is corresponding to a 0, 1 vector, so I will sort of switch sometimes back and forth. The property of submodularity is that for any coordinate j, when you look at the discrete derivative in that direction j, this discrete derivative is non-increasing. If you go to a larger set or to a point which is higher up in the cube, it can only decrease. So that's what it means to be submodular. A function is subadditive if the value of a union of two sets cannot be more than the sum of the two values. It's very simple. And then there's a fractional version of this condition, which is that if you can cover a certain set T fractionally by sets Si with certain multipliers alpha I in this fashion, then the value of T is bounded by the corresponding linear combination of the values of Si. So this is called fractionally subadditive. This is a stronger assumption. Yeah, it's a smaller class. It's a subclass of subadditive functions. And then there's one more notion which actually happens to be equivalent to fractional subadditivity, which is the class of Xos functions. And these are functions that are defined as a maximum over a collection of linear functions with non-negative coefficients. So this is actually pretty similar to something that came up in another talk here, like suprema of random processes. These are random variables, and I take the max over some collection of linear functions. So it's known that this is exactly equivalent to being fractionally subadditive. And at least for monotone functions, there's one point that these functions are always monotone. They can only increase. Submodular functions don't have to be monotone. But if you assume that the function is monotone, that we have this chain, that submodular functions are contained in Xos, which is equal to fractionally subadditive, and these are contained in subadditive functions. Now there's one more class that I want to mention, which is the class of self-bounding functions. So this is a class that comes from probability theory, and it's defined as follows. It's more generally on product spaces. It should satisfy the following property that for any point x, when I take the coordinates one by one, and I try to flip each coordinate to decrease the value of the function as much as possible, this is what this operation does. And I add up the differences, it should be bounded by the value of x itself. That's what it means to be self-bounding. More generally, we talk about A self-bounding functions where you have some multiplier here. So these functions are really interesting because they satisfy the following concentration property. That they are concentrated, they basically satisfy the same Chernoff bound that sums of independent random variables would satisfy. In particular, the concentration is dimension-free. That's a very powerful property of this. So no matter what the number of variables, the value, if the function is 1 Lipschitz, will be concentrated around the expectation in a window which is roughly square root of the expectation. And the tails are like this. There's some asymmetry there. And these functions are also related to the other classes in the following sense. These functions are more general. So Xos functions are 1 self-bounding, and submodular functions are 2 self-bounding. The 2 is just because of the possible non-monotonicity of the function. If you take a monotone submodular function, then it's 1 self-bounding. All right, so this is the landscape of these functions. Any questions before I move on?
The self-bounding definition, why there is no absolute value?
Well, so you always try to decrease. Actually, I should say one more thing about this. So I don't have to make it absolute value because I always try to decrease, so it's non-negative. And one nice example of these functions are so-called configuration functions defined by Talleyrand. So assume that I have a function which has the property that if the value is k, then there are only k bits by flipping which I'm able to decrease the value of the function. So such a function will satisfy this property. And in fact, this theorem implies pretty easily Talleyrand's inequality. So this technique is more general than Talleyrand's inequality for concentration bounds.
So K would then be A there? I'm trying to contract.
No, it would be 1.
No. So A, make it just equal to 1 for now.
K is the value of f.
Yeah, K is the value of f. So it's like a function that counts the appearance of a certain pattern, like what is the maximum increasing subsequence or something like that. So if it's K, then there are K coordinates which certify that that's the case. And when you look at this expression, there are only K coordinates where I'm able to decrease the value by flipping that coordinate. It's more generally on, D could be anything, and you take the product space. In this talk, it's just 0, 1. But this is more general.
And on the next slide, when you wrote just self-bounding, you meant 1?
Yes. Sorry. So usually when you say self-bounding, it means 1 self-bounding. There's also AB self-bounding, but let me not go into that. Anyway, so these are the relationships. And okay, what is this talk about? So this was initiated by the question of how well can we learn these functions when you have a stream of random examples. How well we can approximate the actual function. And this was initiated by Balkan and Harvey, who asked the question for submodular functions. They gave a certain simple learning algorithm, which basically just returns the expectation, and they proved that these functions are nicely concentrated. They actually didn't know about the connection with self-bounding functions, so these things emerged gradually. They also proved that it's more or less hopeless to learn these functions under arbitrary distributions. So from now on, let me just talk about the uniform distribution. Another interesting paper was by Gupta et al., who had an application in differential privacy. Let me not describe that. They had an idea which proved useful in the following work, which was that you can decompose these functions. You can basically decompose the cube into regions where the function is Lipschitz with some very small epsilon Lipschitz. And if you know that, then the concentration bounds imply that it's very well approximated by its expectation. So this kind of approach can refine the degree to which we can approximate the function. Of course, you pay some price in terms of how many subcubes you need. Now, there's this interesting paper, which I think was the first paper that made a connection between Fourier analysis and submodular functions, which was sort of to be discovered out there, not very complicated, but they made the first connection, and they proved that essentially the Fourier spectrum is quite heavily concentrated on the low levels. If you want an epsilon approximation, it's enough to take the first 1 over epsilon squared levels of Fourier coefficients and chop off everything above that. That gives you an epsilon approximation. In L2, now I'm talking about L2 approximations. And they gave a learning algorithm based on that. So by the way, Vitaly will give a talk here at some point, I think at the end of October after Fox, where he will talk more about the learning part of this. So I'm not going to describe any learning techniques, learning results, I'm just focusing on the existential part of this. Following that, there was this line of work on discrete submodular functions. So what that means is functions that are only allowed to take values from some discrete set like multiples of 1 over k. I'm mentioning it here mainly because they were the first who proved the existence of some sort of junta for these functions. And the size of the junta is roughly k to the k, with some epsilons involved as well. So they basically asked the question, how well can we approximate these functions by juntas? And there's a natural connection, because if you know that you can approximate well and you can also discover what the variables are, then you can learn the function well. So that's a natural question in this context. And last summer, we did some work with Vitaly and Pravesh Kotari, where we proved that submodular functions can be approximated by decision trees of low depth, 1 over epsilon squared. As a consequence, this also gives you junta of size 2 to the 1 over epsilon squared, and then we had a learning algorithm based on that, which improves the dependence on epsilon in this fashion compared to previous work. But the questions I want to address in this talk are more on the existential side. What are the juntas that are actually optimal in this setting? And also, why is this work really about submodular functions? Is it that we need this condition, which is quite restrictive? Submodular functions are quite heavily restricted. So why is it that all these papers are about submodular functions? Isn't it really about something else? And specifically, when you see these juntas of size 2 to the 1 over epsilon, it looks suspicious. Isn't there Friedgut in the background, really? So that's the question we want to ask here. And also, how far can we really push these results? So the answers that we give in this paper are as follows. As far as these juntas are concerned, exponentially in 1 over epsilon squared, it is really about Friedgut's theorem. So there's nothing very new in these results. They can be explained by a real valued version of Friedgut's theorem. But there's a little bit that we had to do, and I'm curious if people here will tell me that this was known and written up somewhere. We couldn't really find it, but I will show you a version of Friedgut's theorem which holds for real valued functions, and it implies what we need. So there's an issue with how you measure the influences. Yeah. So I will show that statement, and let's see. It's an easy proof. It's an easy proof. Now, the more novel part of what we did was that we show that there's a big jump between Xos and submodular functions. So for submodular, you can actually do much better. You can find Juntas which are roughly 1 over epsilon squared variables. So there's an exponential jump. And also for Xos, it's necessary to use exponentially many variables. So there's a big gap there. And this proof is completely different. I will get to that, hopefully. We also have applications in learning, but maybe let me just skip that, because I already wasted some time. So this is the picture again with the pretty much optimal sizes of Juntas that you can achieve for these classes. The divide is between submodular functions and these bigger classes.
Are all these sizes tight? These are all
Pretty-
upper bounds, right?
Yeah, but they're pretty much tight. Yeah. So, for example, this size of Junta, you need that even for linear functions, like additive. If you have a function which just adds up the 1 over epsilon squared variables, you have to use almost all of them to approximate. Yeah. So this is, yeah. And for Xos, I will mention that later, but this is tight up to this exponent of 2. We don't quite know if that's
So
optimal.
Xos is the most general class, A self-bound.
Xos is
So the
like-
picture shows how they relate. So monotone submodular is the most special thing. Xos is, in some sense, more complicated than submodular, but it's always monotone, so it doesn't comprise all submodular functions. This piece here is only because they could be non-monotone.
And what does the red X?
Good. So that will be the next slide. For subadditive functions, there's no Junta approximation essentially for simple reason, which I will show. So subadditive functions are, actually it's not a very nice class in my opinion, and let me show you why. So any function which attains values only 1/2 and 1 is subadditive, okay? So it's not a very restrictive condition, actually, in this setting. I mean, maybe for some other problems, it makes sense, but here it doesn't really constrain the function at all. So let's just forget about subadditive functions. It's not an interesting class. So how should I plan my remaining time? I was supposed to.
You still have 32, 33 minutes.
Oh, that's a lot. That's too much. So I'm not going to. I'm not going to keep you that long. Good. So I want to explain two things. One is the connection with Friedgut's theorem, and in particular this real value Friedgut theorem. And the second thing is the stronger bound for submodular functions, which is proved by a different technique, and it's kind of new. Okay. So again, for Boolean functions, we measure the total influence just by adding up these probabilities of whether the function value differs or not. And there's a nice expression in terms of Fourier coefficients for this. So when we want to go from Boolean values to real value functions that have real values, what is the most natural thing to generalize this? One would say that probably by taking this formula, because it's all about Fourier analysis. This is a nice general formula. So we can define that for any real valued function, and that it feels like this is what it should be. But unfortunately, Friedgut's theorem actually does not hold, which is widely known, I guess. There's an example in a paper by O'Donnell and Cervedio. And the example is like this. It's basically a smooth kind of majority function. So the function stays at -1, and then in a window of size square root n, it goes linearly. It only depends on the sum of the xi's. It's a symmetric function. It goes from -1 to 1 linearly, and then it stays at +1. Okay, so what's the problem here? The discrete derivatives are essentially 1 over square root n. No variable can change the value by more than 1 over square root n. So when you look at these squared influences, the squared differences are 1 over n. And the total squared influence would be a constant, right? So it looks like if Friedgood's theorem were supposed to be true, then there should be epsilon approximate junta of size 2 to the something. At least it should be constant for constant epsilon. But that's not the case here. You cannot approximate this function for some constant epsilon, I don't know, 1 over 10. You need linearly many variables. So something is wrong here. And well, so there was this paper by Ryan and Rocco where it was about learning decision trees. And they had a workaround which was essentially to discretize the range. So they said, okay, let's round up the values to multiples of some small delta, and then let's prove Junta approximation for these kinds of functions. So that's true, that works. There's some dependence of delta, which is not too bad. But it doesn't work very well for our setting. For one thing, if you take a function and you round it to multiples of some small delta, typically it's not going to be submodular anymore, and the total influence could actually go up by doing this. So it's not clear how to use that, and also it doesn't feel, I don't know, it doesn't really feel like the right way to state this theorem. So okay, so what we did was we modified the proof, which is really the same proof, to get a statement about the real valued functions, which I will show on the next slide. But before I get to that, just notice that if we look at, let me call these degree kappa influences. So I define, let's just remember this, the degree kappa influences are the expectations of absolute differences raised to the power of kappa. There's no root here. There's no 1 over kappa. Let's just remember that. I'm defining it for kappa because I will use that later. But for this example, just by looking at the L1 influences, these are actually quite big. They're 1 over square root n. I have n of them, so they add up to square root n. So there's no problem in the sense that this is not the function that we would expect to have a good Junta approximation. And okay, here's one statement that you can prove. There's some flexibility in terms of what kappa you use, but I think this is the easiest one to remember. Basically, for any real valued function, there's a Junta which depends exponentially on the squared influences, and then it depends polynomially on the L1 influences. So there must be some dependence on something other than the squared influences, because we know that these are not enough to get a nice result. But the dependence on, let's say, the L1 influences is pretty mild. It's just polynomial. So this is the kind of statement that you can prove, and I mean, I'm not going to claim it as our result. It's the same proof, but I think it's good to write it down, so to have it written down. Some notes, this infl 1, you can replace this by any power strictly less than 2, but not squared. For Boolean functions, this doesn't make any difference. These are all the same. And the point for our original purpose is that these classes of functions that we like, they have small influences in both senses, actually for any kappa. Between 1 and 2, they can be bounded nicely. So, fine? I'll go on.
But for submodular, there must be some other theorem that you don't use the.
Sure. So this is the first part of the talk. In the last 5 minutes, I'll cover the second part of the talk. Actually, I have some time, right?
Like,
Yeah. So, okay, so the proof of Friedgut's theorem, most people here know it. We have to remember how it works. And there are very small differences between what we do and the original proof, or rather, this is like the proof from Ryan O'Donnell's lecture notes, which is pretty clean and nice. Let me just point out, so we defined the junta by taking variables where the influence is large in some sense, and that's defined by looking at the kappa powered influence for some reasonable value of kappa. We pick 4/3. That's not very important. There's also degree bound, which depends on the squared influences. So we still need that to chop off the high degree coefficients. And that's why it depends on both kinds of influences. And the goal is to prove that preserving only the coefficients that live inside the set and they also are bounded by D is enough, that this approximates your function well. So there are two kinds of coefficients that we chop off. The large degree coefficients above D, this is completely standard. This is just bound based on the squared influences. So we chop them off. That doesn't create much error. And then the coefficients which are inside, which are possibly not inside J, they're smaller than D, but they have something outside of J. We have to bound those, and that's where the hypercontractive inequality comes in. So what's going on here? We need, after using the hypercontractive inequality, we need some kind of bound on the L kappa norm of something. That something is the discrete derivative of f. So we need some handle on that, and in the Boolean case, these powers don't really matter, so you can just use L1 or L2, it doesn't matter. But here we have to put it in the theorem. So that's the reason why the theorem depends on some other notion of influence as well. And if you just assume that, let's say, the influences raised to the power of 4/3 are small, that's enough to make it work. Just one more point. Why does it depend exponentially on the L2 influences? Because that comes from D. D is the degree above which we kill all the coefficients. And there's a term coming from introducing the noise operator, which is exponential in D. So we need to kill that, and that part depends on the squared influences. But then the remaining parts are easier to handle. It's enough to be polynomial in the other influence, like the 4/3 influence. So I think this is pretty clear. Okay? All right. Now, why is this useful for self-bounding functions? This is a very simple connection, but I think it's also easy, nice to make explicit. So for self-bounding function, let's say for now it's restricted to the 0-1 interval, the values. You can bound, let's say, the L1 influences by the value of the function itself, the expected value of the function itself. It's a very simple double counting because in the definition of self-bounding functions, we only count the differences where the value goes down. But then you take the expectation over the entire hypercube, so you will count each of these differences at some point. There's just a factor of 2 involved. So L1 or L2 influences for these functions are always small. That's why it works. Okay, so this kind of explains these earlier results and extends them to some other classes, but it's really all about Friedgut's theorem. So now to the last part. Oh, one more thing. So there was a question about tightness. And for Xos functions, we can set up an example which is essentially the tribes function. You just make it Xos instead of DNF formula. So it's a max over sums. And for these functions, we need 2 to the 1 over epsilon variables to approximate them well. So that's why it's tight. Okay, so now this stronger junta for submodular functions. So the claim is that it's enough to pick 1 over epsilon squared times log 1 over epsilon variables to approximate these functions with an epsilon. And you would need 1 over epsilon squared even for linear functions, as I mentioned. You can check that. It's just the standard deviation of sum of independent random variables. So in that sense, submodular functions are kind of very simple. They're like linear functions. There's a big gap between submodular and the other classes. Let me just say the connection with concentration bounds. So concentration is like saying how well is the function approximated by junta of 0 variables, right? Constant. So in terms of approximation by constants, all these functions seem to behave the same way. All the way from linear functions to self-bounding functions, we have very similar bounds, essentially the Chernoff bound. Very similar bounds. So in this sense, they are very similar. But if you try to approximate by juntas of slightly larger size, this big gap emerges between submodular and Xos. So, okay, so how do we prove this? So the proof is an inductive proof. The basic step is to prove that if you have a function of n variables, then I can replace it by a function that depends only on 1 over epsilon squared times log n variables, and the error is bounded by epsilon. There's something like 1/2 epsilon. So then we will produce this sequence of jumps where the size of the junta shrinks, and we arrange the errors. They add up to epsilon. In fact, you don't even have to do that because we already knew from the previous result that there's a junta of size 2 to the 1 over epsilon squared. So if you plug that in here, you get 1 over epsilon squared times 1 over epsilon squared. So in one step, you make it 1 over epsilon to the 4. You do it one more time, and you get what you need. So this is just to make it a standalone proof. So I just have to explain how you make this one step from n to 1 over epsilon squared log n. Let's just do it for monotone submodular functions. So the idea is to run some kind of greedy algorithm, because greedy algorithms are what works for submodular functions. But it's a different kind of greedy algorithm. So the algorithm picks variables. And the way you pick these variables is that naturally you want to pick variables that contribute significantly to the set that you have already, in the sense that the discrete derivative along that variable is large enough in some sense. So the key is to define carefully what it means to be large enough. Now here's one proposal is to look at the set of variables that we have so far, pick a uniformly random assignment and measure the expected discrete derivative with respect to that random assignment. And let's say if it's large enough, then we include that variable. Now this looks maybe promising because we cannot include too many variables this way. The value would just accumulate too much. And the purpose of doing this is that the function should be alpha Lipschitz in the variables that we did not choose. So hopefully it will be nicely concentrated there. This doesn't quite work, and the reason is that the condition of Lipschitzness in these remaining variables is in expectation in some sense. It's in expectation over the assignments to the variables that we already chose. What we really want is a statement with high probability over these assignments and for all the variables outside of our set at the same time. So we need some kind of union bound here. So the goal is that we want to make the probability of failure, the probability that this contribution is large enough, we want to make that really tiny. And just by looking at expectations, we get Markov bound or something pretty weak. So how do we make it very tiny? And here's where we use this lemma from my old days at MIT. So with Michel Gomez, we had this little lemma for down-closed events on the cube. The lemma says that if you have a down-closed event and you look at the probability of this event under a p-biased product distribution, then the probability of this event should decay quite rapidly. And specifically, when you look at it as a function of p, it should be a function which looks like 1 minus p to something that can only increase with p. Does it make sense? This is it's not very hard to prove, actually.
This is for every monotone set.
Yep.
There's no submodularity.
No. This is just, the only condition is that if something is in the set, then everything below that is also in the set.
So for the non-monotone submodular case, you need something.
Well, so this actually applies to the discrete derivatives. So we will use the fact that the discrete derivatives are monotone. Yeah.
Sometimes this is should be related to the Kruskal potency.
Yes, that is a good point. Yeah, so we don't use it, we don't prove it using Kruskal-Katona. Initially we had some, actually slightly weaker version.
Is it closer
If-
to the Russo-Margulis lemma?
No, I don't think
So,
so.
so the proof is not as simple as, let's say,
You basically, you prove it by induction on the size of the ground set. You look at it, you differentiate this function, and you get some kind of induction on the size of the ground set, and you prove that this function has to be non-decreasing. It's not very complicated, but it's a good point.
Phi of p depends on your set?
Yes, yeah,
Phi of p
certainly.
is not a fixed one.
No. So the statement should be, there exists a function phi of p such that the function is in this form.
Maybe log of sigma over.
Yeah.
P is monotone.
Exactly, yeah. It's okay. It's a little bit cryptic, but let me say an example which makes it more clear how we want to use it and why it's called, well, we call it boosting lemma. There's nothing, no relation with like boosting and learning, so people criticized it for that reason. But,
That's the worst criticism you get on your work. You should be very happy.
well, this particular piece. So here's an application of the lemma which makes it more clear, I think. So suppose you have some down monotone event f, and first I look at the uniform distribution. I sample with probability 1/2, and I look at the probability of my event. Suppose I know that it's at least 1 over 2 to the k for some k, so relatively small. So then the lemma says that if I sample instead with probability 1 over k, the probability that the event happens will go up to a constant. So from an exponentially small probability of the event, I go to a constant, and the price is not too bad. I just replace 1/2 by 1 over k. And that's why we call it boosting lemma. In fact, for an integer k, the proof of this is very easy. I'll leave it as an exercise. So, okay. So I'm very happy I can promote this lemma one more time because I gave a talk here actually in 2005 at MSRI about this lemma, but I doubt that anybody remembers. So let me finish.
Can you roll back a second? I'm not quite understanding.
Uh-huh.
Phi has to be separately controlled. I'm not quite sure what.
So the statement is that there exists some non-decreasing function phi such that the function, the probability is in this form. It's 1 minus p to something that can only, it can only increase. Sorry, maybe I made a mistake.
Yeah, so now in this case, you showed that sigma actually goes up.
So now I'm moving from p equal to 1/2 to some smaller value. moving to a smaller value of p. So the lemma says that this function.
Good.
Uh,
Yeah.
now you confuse me.
No,
Yeah,
okay.
you went-
That's better, now I understand.
Yeah, maybe the Mago of Ulema, I mean,
Uh-huh.
this would not directly, if you take Ulema plus the isoperimetric inequality, which says that the sum of influence is always greater or equal to the measure times log 1 over the measure,
Oh,
then,
okay,
then,
but these are like pretty heavy tools for this. This is very simple.
yeah, yeah.
Yeah.
But this is also like a set by set claim, right? So it's somehow the point is that if the set is really tiny, then, I mean, if phi is really large for a specific set, then we learn a lot about it in other values, right? So it's not clear how you can use some general machinery to recover that, right? So,
You can go from one point to another point. Yeah. If I know the probability for some p, then I know that if I go to one side, it will be increasing quite rapidly. Yeah. Kruskal-Katona is closer to this, but we had some version of this which is somewhat weaker in the parameters, which uses Kruskal-Katona. I'm forgetting the details now, but it was a little bit weaker. Yeah, so how do we use this? So we build the set, we build the junta, right? And we build it by checking these discrete derivatives with respect to a random assignment of the variables so far, where we set variables to 1 with probability delta, or some pretty small delta, like 1 over log n. And we include the element only if the discrete derivative is large enough with constant probability. Okay, so the point is that the elements that we did not include, they have the property that with respect to this biased random assignment, the discrete derivative is large with some bounded probability, 1 over e. But it's under a biased measure with this bias, like 1 over log n. So when we move from delta of this value to 1/2, we will actually make this probability very small. So we're using it in reverse now. If I knew, and I'm using the fact that this is a down-closed event. If the discrete derivative is at least something for a certain point, then with respect to a smaller point, it can be only larger. That's exactly the definition of submodularity. So we get a down-closed event here, and what I really care about is the probability over a uniform distribution, because that's my target. So over the uniform distribution, the probabilities of these events for any coordinate that I did not pick to be in the junta will actually be very small. The parameters are chosen so that this becomes epsilon over n. So I pay. That's why somehow we save. Well, we save a lot because it's enough to make the probability 1 over log n, but the probability of the event that I care about becomes epsilon over n, so that I can do a union bound. So we do a union bound over all the variables that we did not pick, and the probability is still bounded by epsilon. Does that make sense? So just to wrap up, we constructed some set of variables such that with probability 1 minus epsilon over assignments to these variables, when I look at the remaining variables, the function is epsilon squared Lipschitz. So we get a very nice concentration there. And this implies that it's enough to fix these variables, average out everything else, and you get an epsilon approximation to your original function. And the size of the junta is actually quite simple to bound. So intuitively, it's the same thing. We include only the variables that contribute sufficiently enough to the current set So the expectation of a certain set keeps increasing every time we include something. We cannot increase too many times. And it's 1 over epsilon squared. So I think I'll just finish. Okay. Sorry. So let me advertise a talk by Vitaly Feldman. I think there's like a day after Fox or something with talks, longer talks. So he will talk more about the learning aspect.
Where is this talk?
So I think it's here at Simon's, right?
So the day after, Wednesday, the day after Fox, there are 3 or 4 somehow carefully selected Fox talks on a longer 50-minute presentation.
So Alexandra organized it. She sent the name.
It's like some papers from Fox related to Boolean analysis, something like that. So so he will talk more about the learning aspect. There's also a question here, open question. So actually, the original question that Balkan and Harvey asked was, how well can you approximate these functions if you want to achieve a multiplicative approximation within 1 plus epsilon up to a set of measure epsilon in the cube. And these techniques imply such a junta, but only for monotone submodular functions. So pretty much the same kind of junta can actually approximate the function up to a multiplicative error, which is more difficult. But then there's some epsilon fraction of points where we don't have any guarantee at all. And that's the so-called PMAC model of Balkan and Harvey. So we don't know if this kind of junta exists for non-monotone submodular functions or not. There might be a gap between these two. All right, so that's all. Thank you.
So this multiplicative thing, can you get it from the alpha approximation for modular, or is it just the proof, you follow the proof? And
Yeah, you modify the proof.
Okay.
We have actually several ways. There are 2 ways. One uses the additive one as a black box, but then the parameters are slightly worse. You can modify the proof to give you the multiplicative junta.
The other thing is more of a remark is that, so Talleyrand has this paper similar to KKL for PYS, and there he looks at this L2 versus L1 thing for the influences, and so, I mean, he shows that if the total influence is small, then you get some variables with large L2 versus L1, which I think
Oh, so maybe it is
similar,
written up.
but it doesn't
somewhere.
have this kind of junta theorem there. And also he looks at some other norms, actually not L1. So, so as you said, you can look at this kappa for any value less than 2, right?
Yeah.
And there is a stronger thing between these LP norms and L2 norm, and that's kind of the bound where the proof fails. So probably.
So what is the statement there?
So you can measure you can define an influence not with LP norm, it's with a different norm, which is stronger than all these LP norms for P less than 2. But still the proof works for that.
So you get a junta as a result, or what is the
you get
purpose?
variables with large influences.
So
So probably.
it's like
large
KKL,
junta.
and if that works, this should work too.
Yeah.
Yeah.
So
so like-
Orlitz's norm?
What is the norm?
Orlitz's norm?
Yeah, I think it's somewhere, some Orlitz's norm.
I see.
Have again.